So for the first talk, we are happy to have Po-Shen Hsin from King's College London, who will tell us about automorphism is all you need, transversal non-Clifford gaze in 2+1D, and higher symmetry.
Okay, thanks for the introduction. And I would like to thank the organizers for putting together such a wonderful conference and having me here. So today I'm going to talk about a new construction of transversal non-Clifford logical gaze. So it's a topic in continuation to Shenjie's talk yesterday. And also I'm going to talk about how higher symmetry and those non-Clifford gaze can arise by group automorphism. Okay, and the talk will be based on two upcoming works. So one of them will come out next week in collaboration with my wonderful collaborators. So Ryohei Kobayashi, who is also here. So he's applying for a job, so please hire him. And also Guanyu Zhu from IBM. There are also related works I will mention briefly. So there are works with Mason Berkashli and also Ryohei here, and also with Xiechen Arpit, Chaoming Chen Ke. Okay, so maybe let me just backstep a little bit. So because we have a mixed audience, so let me just give a very brief introduction to quantum computation. So why do we care about quantum computation? So quantum computers has the ability to simulate classical simulate quantum dynamics exponentially faster than quantum computers. Than classical computers. So the reason is that the dimension of the Hilbert space will scale up like exponentially faster if you increase the system size. So the computation resource become demanding for classical computers to do this kind of simulation. But quantum computers is a natural place to run those simulation for quantum dynamics. So we can use quantum computers to, in particular, we can use quantum computers to tackle simulation problems in higher dimensions, such as like 2+1D or higher. And and some people also use quantum computers to tackle quantum chemistry simulation problems that can potentially lead to new discovery of like materials or medicines. And people also use quantum computers to study new encryption methods that are more secure, and also some optimization problems for complex data, such as IBM has been doing this to optimize finance portfolio. Okay, so let me just give you a brief history of quantum computation. So it's invented by a physicist, Manning and Feynman, who suggested that quantum computers can simulate quantum dynamics exponentially faster than classical computers. So that's something I already mentioned.
He's a mathematician.
Oh, sorry, yeah. Oh, yeah. Mathematician and physicist, yeah. And also, as Zheng Han mentioned yesterday, there are many great discoveries made by Peter Shor. In particular, he discovered the first error correcting code, the famous Shor code. And later on, Kitaf discovered the surface code, which is later on related to topological gauge theory. So that's the first time where gauge theory comes into play that is relevant for quantum computing. So he discussed how to use onions to do logical gates in this kind of quantum computers. And later on, there are threshold theorems, which Zheng Han mentioned yesterday, that are discovered by Kitaf and also Neil, Laflamme, and Dvorak. Okay. And later on, Zheng Han and other people discovered that you can use non-abelian onion braiding to perform universal quantum computation. And let me just skip the history in the middle. So there are also many recent development. So in particular, there is a discovery of a Goulart BC code. So it's a quantum code that can be that's very efficient. So it has the potential to be practically implementable on scalable quantum computers. And more recently, there are progress in experiments such as on Google's, which can manage to reach the threshold. So when you scale up your quantum computers, you actually reduce your logical errors. And more recently, there are progress made by Microsoft and also Google's. Okay. So that's a brief history. So now let me give you some just basic introduction to what is the basic components of quantum computers. So the idea of quantum computers is basically replacing like classical bits like 0 and 1 by different quantum states. So like 0 bit by one state and 1 bit by another orthogonal quantum state. And we want to encode the logical information as the ground state wave function of some many-body lattice models that have many physical qubits. And just as on classical computers, you have a memory that can read and write. On quantum computers, you also have quantum memory. But here we have to be careful because in quantum mechanics, we have fluctuations. So we want the quantum memory to have the ability to store the logical qubits and maintain the coherence, such as via error corrections. And just as a classical memory can read and write, we want a quantum memory to be able to perform logical gates. Those are the computations on your quantum computers. So they are unitary operators acting on these quantum states that represent the, yeah.
I want to understand the difference. What is the physical qubits?
Sorry,
physical qubits.
Right, so if you have a many-body lattice model, and the physical qubit can be like on each place locally on your lattice model. So the idea is to protect your logical qubit by some repetition. So you have one single logical qubit that is represented by a wave function of many physical qubits. So this kind of repetition can protect your logical qubits via error correction. So that's the idea. So when you try to build your quantum computers, you want to so for example, you can try to have many physical qubits that can represent your sort of many-body lattice model. And then the wave function, the ground state wave function, is your logical qubit.
So indeed, you want to say that you just can use the NKD to estimate how many errors can be corrected. That's right.
So let me go to that. So one important characterization of the performance of quantum code is this NKD number. So N is the total number of the physical qubits. It's like total number of like lattice sites, and K is the total number of logical qubits. It's the how many ground states you have in your many-body lattice model, and D is the is called a distance, and it is the number of errors that you can correct in your quantum code. So D is the distance. So for example, for the Tori code that Sanjay talked about yesterday, N is the total number of edges in your lattice model. And K for a torus, it will be 4. And this is because there are 2 independent one cycles on a torus. So we have 2 independent one cycles, and each of them encodes a logical qubit. So logical qubits is like 2 dimension. So 2 to the power 2 equal to 4. So this is K. And D will be the linear size of your torus in your lattice model. So let's say NKD for the Tori code that Shenjie mentioned yesterday. So I will also briefly review Tori code today. Is there any question? Okay. So how does symmetry come to play? So let's consider an emergent symmetry of your many-body lattice model. So the symmetry is an emergent symmetry. It means that it preserves the low-energy ground state subspace. And because, as I mentioned earlier, the ground state of your many-body lattice model describes the logical qubits, so symmetry also provides logical gates acting on logical qubits. So one example is that if you take 2 identical code blocks, so they are just purely identical, and then you consider a symmetry that just exchange like every physical qubits within these two layers, then naturally you will also exchange the 2 logical qubits. You will also exchange the one ground state wave function of these 2 copies of the lattice model. So it's so-called a swap gate for the logical qubits in this model, and this swap is a symmetry. Now we want the logical gate, you want the logical gate to be fault tolerant. So suppose you have an error. So as I mentioned earlier, the logical qubits are the ground states. So errors will be excitations that take you away from the ground state. So let's see. Okay, so let's say you have an error here. You have some 1D lattice, and you have an error here. This is some excitation. After you apply the logical gate, you don't want the error to spread too far. Okay. So you can represent the logical gate, so which is a unitary operator, by the product of like a bunch of small unitary operators, like on some neighboring sites. Okay. So as long as the depth of this circuit is finite, the spread of this error will also be finite. That does not grow with the system size. So if the logical gate consists of a symmetry, which is described by a finite depth circuit, so the finite depth means that this width or the depth of this circuit is finite, then the logical gates will be fault tolerant. And in this talk, I'm going to refer to this kind of finite depth circuit as giving rise to transversal gates. So some people also refer to transversal gates as strictly on-site symmetry, but here I'm going to refer more broadly, transversal gates as a finite depth circuit because they have similar error threshold property.
Okay, I also want to ask one technical question. So what is locality preserving of the symmetry generator? Here just say error does not span too much. What do you mean for?
Right. Now let me give you a counter example of not preserved. So let's say you have error here. You apply a symmetry. The error just spread to entire space. So there's some kind of, so suppose you have some kind of non-local symmetry that can sort of interact between like side here and side very far away.
So when you
Then it
say
does not preserve
local,
locality.
you mean that one side can do interaction to all sides.
For example, that would be non-local. Yeah.
Okay.
So as long as as long as you have a finite spread after you apply the symmetry, then it is locality preserving. Yeah.
Okay, thank you.
Do you know if QCA will be?
Oh yeah, QCA will also, but I'm not going to go cover QCA here. Yeah, but more generally, you can have QCA. Yeah, So so QCA will be the most general unitaries that preserve locality. Yeah, but here I don't need the QCA here. Yeah. Okay, so what are the challenges to construct logical gates? So first of all, if you want to perform all the possible computation, we need non-Clifford gates. So Clifford gates are unitary operators that can map poly operators to poly operators, and they are very restricted set of all the possible unitaries. So in order to perform all the possible unitary operators on your logical qubits, we need some non-Clifford operators. We need some non-Clifford gates. And more importantly, if you want to compete with classical computers, you really need non-Clifford gates because you can already simulate Clifford gates very efficiently on classical computers. So you really need non-Clifford gates to show that you have very advantageous quantum computers. Now, at the same time, we want the logical gates to be very efficient. So for example, we want to reduce the space overhead. So ideally, we want the interaction to be only involve like a finite number of physical qubits that does not as small as possible. So in order for interaction to involve such small number of physical qubits, we want the space dimension to be as low as possible. Otherwise, it might be difficult to construct the quantum codes. And at the same time, we want the logical gates to be fault tolerant. So as I said earlier, ideally, we want the logical gates to be a transversal gate generated by finite depth circuits. Now, however, there are many no-go theorems for polystabilizer codes that tell you it's very hard to find non-Clifford transversal logical gates in low space dimensions. So there are no-go theorems by Isting-Neal and Bravi-Koenig, and also many other follow-ups. So the question I'm going to address today is how to find transversal non-Clifford gates in like low space dimensions, such as two-dimensional lattice. Okay, so this is the main question I'm going to address. So you have seen similar talks yesterday by Shen Jie, but here I'm going to describe transversal logical gates. And also we want to make the model as simple as possible. We want to reduce the overhead for preparing the ground-state wave function. So we want to make the wave function as simple as possible. So that's the general philosophy and the goal. Any questions? Okay. Okay, so as you already heard from Shen Jie yesterday, there is a new route to get the non-Clifford logical gates in low space dimension via non-abelian topological order, so via non-abelian quantum codes. So there are many studies about how to get non-Clifford gates in non-abelian topological orders. Especially there's a new paper just come out this week by Sakura and Shen Jie. There's also an upcoming paper by Tyler and Naren and other people. Okay, so I should also mention that this kind of non-abelian topological order is not far-fetching. It's already been realized in quantum processes. I think it's a few years ago, especially in the paper by Nat and others. And so in order to get a non-abelian topological orders, polystabilizer is definitely not enough because, let me first say what is a polystabilizer. So here the polystabilizers means that you have a Hamiltonian, which is a sum of Hamiltonian terms, and the Hamiltonian terms are mutually commuting, and the Hamiltonian terms are made of products of poly operators. So this is what polystabilizer means. So polystabilizer is a particular many-body lattice model whose Hamiltonian terms is mutually commuting, and also it is each of them is a product of poly operators. So because poly operators, so the commutator of poly operators can only give you a phase. So polystabilizer models cannot give you non-abelian topological orders, and it can only give you abelian topological orders. So it's not sufficient to use polystabilizer. Now, what's the next simplest possible candidate? So let's replace Pauli operators in your Hamiltonian terms by Clifford operators. So instead of Paulis, we can have Clifford operators such as the Hadamard or the phase gate or the CZ. Okay? And in this way, we can get a model that can describe non-abelian topological orders. So I'm going to tell you how to construct the model in a minute. So
if you have a structure just with the Clifford hierarchy, if you pick the stabilizer K and then get the data K plus 1.
Yeah. Okay, and another important ingredient is the automorphism of the gauge group. So I'm going to describe for you later that there is a gauge group that underlies the quantum code. And for groups, there is an automorphism symmetry. So the automorphism symmetry is going to be the hero of the talk today. So you will give rise to those transversal non-Clifford gates. And there are also many other approaches to give rise to non-Clifford gates, such as magic state distillation, like you heard from Shenjie yesterday, and also dimension jump, like jumping to other higher dimension, like code switching, which I'm not going to talk about today. Okay, so this is the outline of the talk. So first, I'm going to tell you how to construct the lattice model. So it's going to be a Clifford stabilizer model on 2D lattice. You can also do it in higher dimension, but then you'll raise the Clifford hierarchy, which Zheng Han already mentioned. And I'm going to talk about the automorphism symmetry in twisted gauge theory. So the gauge theory is going to have a non-trivial cocycle. So this is the name twist means. And this twist is going to render this automorphism symmetry to be some higher group symmetry or some extension or some non-invertible symmetry. So I'm going to talk about those in detail. And then finally, I'm going to use automorphism to construct those transversal non-Clifford gates in 2+1 dimension, including the logical T gate, CS gate, and also CCZ gate in higher dimension. And I'm also going to describe a generalized Bravais conic bomb that tells you what's the possible logical gates you can get in given space dimension.
So you cannot get a H gate in 2+1.
Sorry?
Can you get an H gate, the harder one?
The harm, yeah, of course.
You didn't list it.
I mean, here, right. So here I only list the non-Clifford gates. Yeah, yeah. But for example, in 3+1D, I can run similar construction. I can get the like the R4, like square root of T. Yeah. So it's sort of one. So I can do the non-Clifford gates in sort of one lower dimension compared to the Bravais conic bomb. So this is the idea. Okay. Okay, so let me begin with the construction of the lattice model. So, well, let me first briefly just review what is the toric code that Shenjie mentioned yesterday. So let's consider toric code on a square lattice. So this is a square lattice, and I'm going to have a physical qubit on each edge. So you can think of those physical qubits as well, depends on how you manufacture the qubits. So you can think of it as some small magnets or like some atoms that have two states. That lives on each edge of this square lattice. And the Hamiltonian term, so these physical qubits are acted by Pauli operators, physical Pauli operators on each edge. So the Pauli operators that are the X and Z operators, they anti-commute. And you can think of the Pauli Z operators as labeling the holonomy of a Z2 gauge field on the edges. And because X and Z anti-commute, the Pauli X operator will be the electric field. Sorry. Will be the electric field which canonically conjugate the gauge field. Okay. So, and the Hamiltonian is a sum of two types of term. So one type of term, which I call AV here, is for each vertex. So for each vertex, you take the product of four Pauli X operators that nearby the vertex. And also for each phase or for each plaquette, you take the product of four small Pauli Z operators on the edges that surround the plaquette or surround the face. So this is a small holonomy of your theory, and you can also express this vertex term, which is product of 4x, as the divergence of the electric field. So recall that x is related to electric field. So this first term becomes the Gauss law term. You capture whether Gauss law is violated, namely whether there are electric charges there. And the second term is a small holonomy around the face, which captures whether there are fluxes around the faces. Okay. So this is the model, and you can check that they are mutually commuting. So each of them is each term in the Hamiltonian is a product of Pauli operators. So it's a polystabilizer model. And because of those physical interpretation, the ground state of the model will be described by a Z2 gauge theory, or a topological flat Z2 gauge theory, where on any contractible loop you don't have any holonomy and you don't have any charge in the vacuum. Okay, so the ground state will describe Z2 gauge theory. And the ground state subspace is described by the holonomy of those Z2 gauge fields. So if you consider periodic lattice, so if you identify left and right, and also identify the top and bottom, the lattice has the topology of the torus. Then there are two independent one cycles on this torus, and that gives rise to two logical qubits. So the holonomy can be 0 and 1, and you have two independent one cycles. So you have like 4 possibilities, like 2 to the power 2 possibilities. So this is the logical qubits for this model. And the model has a Wilson operators. So if you can take a product of poly-Z operators along a string, along a closed loop on the lattice, and this gives you a symmetry that commute with the Hamiltonian. And similarly, you can take a product of poly-X operator along a closed loop on the dual lattice, and this X-string operator, X-loop operator will also commute with the Hamiltonian. It's a symmetry. So that's a very quick introduction to toric code. Okay, so for our model, we are going to take 3 copies of the toric code. So the toric code is a Z2 gauge theory. We have 3 of them, so there are 3 gauge fields. I'm going to call them RGB, so like red, green, and blue. So you have to visualize in your head. This is red, this is green, this is blue. So we have 3 gauge fields, and they are coupled together by interaction. So the interaction, so this interaction couples the 3 gauge field together by something called cut product. So for this talk, you can think of them as a wedge product for now. Okay, so it's like so we have a 2+1D theory. So this is why you have a 3 co-cycle. That is the wedge product, sort of for the 3 one-fold gauge fields. Okay, so this is a coupling. And we can also include the dual gauge field, or the Lagrangian multiplier gauge field, which I denote by this tilde. So you have this AR tilde, AG tilde, and AB tilde. And they have the following purpose. So if you integrate out, so if you perform partial integral to integrate out this AR tilde, AG tilde, AB tilde, these extra terms will constrain this AR, AG, AB to have vanishing holonomy when on a contractible loop. So if you have a small loop, those Lagrangian multiplier will force those gauge fields to have vanishing holonomy. Okay, so now let's construct a lattice model for this gauge theory with this co-cycle. So we are going to construct it in 2 steps. So the first step is to construct a lattice model that has a Z2 cube symmetry, and it is a non-trivial symmetry protected topological phase. So a symmetry protected topological phase can be characterized by a group co-cycle, by a 3 co-cycle, which is precisely this co-cycle. And there's a standard procedure as given by by Xie Chen, Zheng Chen Gu, also Xiao Gang, many years ago to construct a commuting projector Hamiltonian lattice model for this kind of group cohomology SPD phases. So there's a standard way to construct the SPD phase lattice model. And after we construct this lattice model with this Z2 cube symmetry for this SPD phase for this co-cycle, we then gauge the Z2 cube symmetry. And that will give us a gauge theory, a Z2 cube gauge theory. So yesterday you already heard from Shenjie how to gauge a symmetry. So this is precisely what we are doing here. So I'm going to spare you all of the details, and I will just tell you the result. So in the end, you got the Clifford stabilized model. So the Hamiltonian term will consist of Clifford gates, and the Clifford gates here is the CZ gate. For example, compared to the let me go back. Okay, so in toric code, this X term is just product of 4 poly X around the vertex. However, for this kind of twisted gauge theory, in addition to product of 4 X's, we also have a product of 2 CZ gates. So CZ gate is a 2 qubit gate. So it acts on the qubit on this edge, on the endpoint of these dashed lines, and also on this other edge, on the other endpoint of the dashed line. So this is a CZ gate that acts on the qubits correspond to the color green and color blue So it has different color from this X here. So you have red X here, and also CZ for the green and blue here, and CZ for the green and blue here. So that's the modification compared to the standard torical. Yeah.
Just so I understand, the theory on the top half, that's already a Z2 cube gauge theory?
The theory on the top half,
What
yeah.
are you gauging?
Right. So So the construction is 2 steps. So first, I construct an auxiliary lattice model for a phase where the Z2 cube is not gauged, but it's a non-trivial symmetry protected topological phase with the Z2 cube global symmetry.
Okay.
And this symmetry protected topological phase is characterized by this cocycle. And there's a standard procedure to construct a lattice model for this SPD phase with the Z2 cube global symmetry. And then I gauge the Z2 cube global symmetry to land on the model we want, where the gauge field has this topological action. And this,
Okay.
yeah. So that's the procedure.
How many qubits on each edge? Is still 1 qubit or 3 qubits?
We have 3 we have red, green, and blue, 3 type of qubit on each edge.
Okay, so there are 3 qubits on each edge.
That's right. Yeah. So right. And also similar to torical, we still have this product of Z terms for each color. So part of red Z, part of blue Z, part of green Z. So it's the same Ploquet term. Okay. So the only terms got modified is the vertex term. Okay. And this is the stabilizer. And the position of this CZ operators can be captured by this. Can think of it as a wedge product. There's some condition, there's some precise way to tell you where to put the CZ operator. And we can define this model on any kind of lattice, but we can stay in square lattice.
Let me
Okay.
ask you a question.
Yeah, sure.
Then. So you put 3 copies of torical on the lattice,
And couple it, yeah.
coupled together. I can just cheat. I can just take 3D torical and push down into 2D. Is there a problem with that construction?
Well, I mean, here we just have purely 2D. So you will have to like get rid of the extra dimension. So you can think of starting from a 3 torical, and you apply something like you apply a CCZ in the middle, and then you push the CCZ down to a bottom, and you get rid of the extra dimension. Yeah, but in order to get rid of extra dimension, you have to like do measurement to get rid of the extra dimension. So that is a bit complicated. So we want to make the space dimension as low as possible. So that's the end here. Okay, so let me just briefly mention that the theory, this lattice model, is actually describing a non-abelian topological order. And this non-abelian topological order is nothing but what Shen already discussed yesterday. This is the DA gauge theory. So here notation DA means that it is a dihedral group of order 8. And okay, let me see. So one way to see this, well, let me just, so one way to see this is that in this model, the product of Pauli X operators around a loop is not a logical operator. So the product of Pauli X operator around a loop does not commute with the Hamiltonian. But rather, if you take a product of this loop, a product of X around a loop, together with product of Z for a different color, and a product of Z for another color, also around the loop, with this kind of projection that decorates this X loop, you got an operator that commute with the Hamiltonian. So without those decoration, though, this X loop does not come with the Hamiltonian. And because of this decoration, this kind of operator will obey non-abelian fusion rule. And this non-abelian fusion rule is precisely the fusion rule for the 2-dimensional iraq of the DA. Okay. So now let me proceed to discuss the automorphism symmetry of the twisted gauge series. So before I do that, are there any further questions? Okay. So here I'm going to discuss a general gauge group G. For simplicity, let me take G to be abelian. And the gauge theory has a topological action described by a group cocycle. So I'm going to use this omega for the group cocycle. And the automorphism is a map from the gauge group to itself. So in this talk, I'm going to talk about abelian groups. So G is abelian. So automorphism will be the same as the auto-automorphism. But in general, we should consider auto-automorphism as the symmetry. So one simple example is when the group is 2 copies of Z2s, then there's exchange automorphism that exchange the two Z2s. And this automorphism will also induce an action on the gauge field. So you will also exchange the gauge field, A1 and A2, for these two Z2s. So here the superscript just means that you are distinguish the two Z2s. Okay. Yeah.
You're not considering the n-wide type things.
No, just purely, yeah. I mean, we can also do that, but let me focus on the just the group automorphism. Yeah. Okay, so what about symmetry? So suppose you have a gauge theory with a non-trivial topological action, then we can ask what happened to those group automorphism? Is it still a symmetry? Is there some modification? So if you have an automorphism that preserves the topological action, that preserves the co-cycle of the gauge group, then you can recover the symmetry. So if the automorphism preserves the cohomology class, then that means that when it applies on the co-cycle, it can only shift it by an exact co-cycle, some d alpha. So let's consider the situation in space-time where you perform this automorphism transformation on the half space-time, and while on the other half, we do not perform the transformation. Now, because on this part, when you perform transformation, omega is shifted by d alpha. So by Stokes theorem, you can recognize that on this domain wall, there's extra e to the I alpha here. So that is telling you that the automorphism symmetry is decorated with this additional factor e to I alpha, which is going to be the main player of this talk. So here, this V rho is just the automorphism action. And this e to I alpha arises because the topological action is not exactly invariant, but it is shifted by an exact co-cycle. So let me give you an example. So let's consider again the Zn times Zn gauge theory. It can take n equal to 2 if you like, in 2+1 dimension. And again, we consider the exchange symmetry, like exchange the two Zns. And you have an action, which is just a mixed transform terms for these two Zns. So let's call the gauge field for those two Zns as A1 and A2. Then the mixed transform term is an integer k over 2 pi and A1 dA2. Now, if you apply this swap automorphism, you will just exchange A1 and A2. But this action is not precisely invariant. You can see that this is only invariant up to a total derivative. Okay? And this total derivative is this e to the I alpha here. So in this gauge theory, the automorphism symmetry is going to come with this additional A1, A2 in the exponent. Okay, so what's the consequence of this modification? So the first modification is how the excitations are permuted. So naively, if you have a gauge theory and you have an automorphism, so the gauge theory has a pure flux excitations. So those are fluxes of the gauge theory, and those fluxes are labeled by the conjugacy classes of the group elements. So they are labeled by the holonomy carried by the fluxes. So naively, an automorphism of the gauge group will just permute the fluxes by themselves, but this is no longer the case if you have topological action. So if you have topological action, the automorphism symmetry is decorated with this e to the I alpha. So when a magnetic flux pierces this automorphism symmetry domain wall with this e to the I alpha, it actually becomes some kind of dynamic flux. So it attaches some electric charge together with this flux. So for example, if you have Zn times Zn gauge theory, this is the example I told you earlier, and the swap symmetry has this extra e to I alpha with this A1, A2, then the swap symmetry will not just simply exchange the flux between the 1 and 2, so this M2 and M1 are the flux, are the pure flux of the Zn gauge fields, but instead it will permute the flux to be some kind of dynamic excitations. So that's one, yeah.
Why you do not find stage bias?
Right, so by itself is not, so this is an important thing. So e to IF by itself is not well defined. E to I alpha by itself is not gauge invariant. Only together, combined with the automorphism action, it becomes a well-defined operator. So this is very, very crucial. Otherwise, you could have removed the e to I alpha by attaching with something well-defined. So the important thing is that you cannot remove e to I alpha, because e to I alpha by itself is not well-defined. Only when it combines with the automorphism, it becomes well-defined.
Why the EM symmetry is broken? It preserves the charge, not the flux.
Right. So here we have a twisted Z2 gauge. Sorry, twisted Zn times Z10 gauge. There's a twist. So without a twist, you have Yen duality. But here we have a twist, so that breaks the Yen duality. Yeah. And you can also see that. So if you do not have a twist, then the flux will have spin 0, and the diamond will have non-trivial spin. So it only works because there's a non-trivial twist. Yeah. Okay. Another consequence is that the symmetry can be extended. Sorry. So the automorphism symmetry is attached to this E to I alpha, and let's consider two automorphisms, rho 1 and rho 2. So at the level of the automorphism group of the group, it can compose into some rho 1, 2. So rho 1, rho 2 can compose into rho 1, 2. It's another automorphism. But the symmetry might not compose according to this composition rule. And in fact, there can be additional symmetry that extend the automorphism symmetry. So automorphism symmetry will now obey the same fusion rule as the automorphism group. So let me give you an example. So let's consider Z2 times Z2 gauge theory. So it's a 2 copies of torical in 1 dimension higher in 3+1 dimension. So the theory has a non-trivial cocycle. So now we have 4 space-time dimension, and it is a 4 cocycle. Here, A1 and A2 are again the gauge fields for the 2 Z2s, and this is your cocycle. And let's consider the automorphism. So this automorphism changed the first Z2. So here, G1, G2 are the elements for the Z2 times Z2. The automorphism changed the first Z2 to be a diagonal Z2. So it changed the G1 to be a combination with G2. And this automorphism for Z2 times Z2 group has a Z2 fusion rule. So if you apply the automorphism twice, you got 1. And if you ask what is the symmetry correspond to automorphism, there is actually a fractional transformation term that is attached to the automorphism symmetry. And this fractional transformation term tells you that the symmetry of the automorphism is not Z2, but instead a Z4 symmetry. So the Z2 automorphism group is extended to be a Z4 symmetry. Okay, so let me also give you another example where the extension does not happen. So whether the extension happens really depends on your automorphism and depends on your cocycle. Okay, so let's consider a twisted Z2 cube gauge theory in 2+1 dimension. So this is the theory underlies the lattice model. So again, it has this cocycle. And if you consider this automorphism that change the middle Z2, the green Z2s, to be sort of a diagonal, a mixture of the 3 Z2s, then again, you can find out the action only changed by an exact cocycle, and the automorphism symmetry is modified by this extra phase. Okay. Now, in this case, the automorphism symmetry is actually still Z2, so this automorphism is Z2. And the automorphism symmetry has this extra alpha, this extra phase. But the automorphism symmetry is still a Z2 symmetry. It is not extended to be Z4. So whether the symmetry is extended really depends on the cocycle, the gauge group, the automorphism. And you can construct an explicit finite depth circuit for this automorphism symmetry in the lattice model. Okay, so let me give you another example where the automorphism symmetry can become a higher group symmetry. So higher group means that it's a mixture between symmetries whose generators have different dimensions. So let's consider 4+1D theory. So it's a 4 space dimension, and the theory is called loop torical. So it's a 2-phone gauge theory, and the gauge group is Z2 times Z2. The gauge field is 2 phones. The gauge fields, let me call them B1 and B2, so those are 2-phone gauge fields. And here I also include a Lagrangian multiplier. You will have B1 tilde and B2 tilde. They are Lagrangian multipliers. So the theory has a Z2 automorphism that again changed the first Z2 to be the diagonal Z2. So you shift the B1 gauge field to be a combination with the B2. And this is an automorphism of the Z2 times Z2 gauge group. Now, however, because the theory has this twist or has this action, under this automorphism, the action is not precisely invariant, but it's changed by an exact cocycle. And therefore, the automorphism symmetry is actually becomes attached. It's actually attached with these extra factors because of the cocycle. And if you apply the automorphism symmetry on for the manifold such as CP2, you actually find that so this is actually 2. So you actually find that they fuse into a membranal pattern. So if you fuse two 4D domain walls for this automorphism symmetry, you actually produce a 2D membranal patterns for a one-phone symmetry. Sorry, for a two-phone symmetry. And this indicates that this kind of mixing between operators of different dimensions is a signature of a higher group symmetry. So in this case, you got a three-group symmetry. And there are similar discussions in my paper with Xie Chen and other people. Okay. Yeah.
How do you determine the oncoming membrane location for the frames?
So I want to ask the exact detail where it happens. So if you look at this expression, so if you fuse two of them, you got the so you got a non-trivial operators, which is a gauge one phone. So it's saying that it is an operators where you have a gauge one phone SPT on the support of the operator on the end that supports the operator. And if you further square it again, this gauge one phone SPT actually has a it has a Z2 classification, so it becomes actually a membrane operator. So instead of a non-trivial operator supporting an M, it actually a non-trivial operator supporting on a membrane. So here, this K here, this kappa here is the integer 2 cycles that dual to the kilophone on CP2.
I understand the last sentence, the dimension. So we are having two 4-dimensional submanifolds in 5 dimensions. It's a fusion 4D domain walls.
Right.
Membrane.
Right.
So
right.
This is done in 5 manifolds.
So the theory is in 5 space-time dimension. You have a domain wall which is 4 dimension. So it's a 4-dimension domain wall within the 4+1D. So you can think of as entire space if you like.
How you get the 2D from 2 4D?
Right. So it depends on geometry. Depends on geometry of the 4D. Yeah. So you always got so same as that. You always got a membrane operator regardless of the topology or geometry of the 4D space. And in this particular example, so that if your space is CP2, you have a integer like 2 cycles, like dual to the kilophone, and this is where the membrane operator is located.
Or you get to the generator.
Yeah, got the generator. Yeah. And for our case, like torus, you actually do not get anything. So, but you always got a membrane operator.
So kappa is dual to W2.
Yeah, kappa is dual to W2. Yeah. More general case, that kappa will be dual to the W2 of the space. Yeah. Okay, so now let's consider another type of higher symmetry, which Shenjie also briefly, it's featured prominently in this workshop. So the automorphism can also give rise to non-invertible symmetry. So let me try to be brief here. So let's consider a case where the automorphism does not preserve the cocycle. So in this case, we can describe the automorphism symmetry as a sandwich. So in the middle, we break the gauge group down to a subgroup such that under this, when you restrict to the subgroup, the automorphism actually preserves the cocycle when you will restrict to this subgroup. So in the middle, we have a subgroup K gauge theory with an invertible symmetry. Here we have a purple interface, which is breaking the gauge group to this subgroup K. So this purple interface is condensation of some electric charge that can break the gauge group down to K. So together, this kind of sandwich describes the automorphism symmetry. And on the lattice, you can explicitly write down the symmetry operator, like you have invertible symmetry in the middle with this extra factor alpha for the K gauge theory. And here you have some projection that breaks the gauge group down to the subgroup K. Okay, let me just quickly give you an example. So let's consider free theory in 3+1D, free Maxwell theory. That's sort of the Faraday theory, like hydrogen theorists like. So you have U1 times U1 gauge theory with this gauge field A1 and A2, and you have this theta term. And depending on the whether theta is 0, pi, or other rational values, you can have an ordinary automorphism symmetry that apply on the gauge field in this way, or the symmetry can become 2 group, or the symmetry can become non-invertible. Okay, so skip this. Okay, so now let me talk about important part. So we have like 50 minutes. Okay, so let's consider this. So let me just go back again, just to remind you what is the model. Okay, so let's consider this Clifford stabilizer model on a finite region with boundaries. Okay, so this is the model, and we are going to put it on the on this region. Okay, we're going to put it on this region, and here I also sketched a few terms in the models. So it has the so it has three boundaries, three different boundaries. So one boundary is the dirichlet boundary, is the rough boundary for the red qubits. So it's the dirichlet boundary condition for the red gauge field. And the other boundary is the rough boundary for the blue qubit, or the dirichlet boundary condition for the blue gauge field. The interesting thing happens on the third boundary. So in the third boundary, we have some kind of mixture boundaries, which is setting the gauge field, the red gauge field, equals to the blue gauge field, and also is the rough boundary condition for the green gauge for the green qubit. Okay, so this is the boundary conditions. Now for these boundary conditions, the Clifford stabilizer models has a single logical qubit. So the single logical qubit is labeled by the holonomy of this equal gauge field on the bottom edge.
You're only connecting one of them.
Yeah, one. Yeah.
So it's not around.
Sorry. So each of the boundaries can be described by a Lagrangian algebra. So you can write down Lagrangian algebra explicitly for the three boundaries. Yeah.
But the three gauge fields, you only said one.
Yeah. So this is right. So here I didn't write down. So here I'm setting the dual gauge field to 0, like sort of. Or you can think of so another way to describe the boundary is the subgroup that is preserved on the boundaries. So I start with the Z2 cube gauge group in the bulk in the center, and in this edge I break the Z2 cube to Z2 times Z2. And for the other edge I break it to Z2 times Z2, and the other edge I also break it to I think a single Z2. So I break the green Z2 completely, but I break the red and blue Z2s to a diagonal Z2. Yeah.
What's the code parameter? What's the NKT?
Well, it depends on geometry. Yeah.
What's the best number you can get?
I mean, here we just have a single logical qubit. So, right. So the distance is like the distance is it will scale linearly with the size. So this is the logical operator. So the size would be your distance. Yeah.
You have 27 in the middle. Do you have any qubits on the edge?
You mean physical qubit or?
Yeah.
Oh yeah. So they are boundary physical qubit. Yeah.
And we also have physical.
Yeah.
So you have like 1,000,000 or something, or 1,000.
I mean, just depends on the size, right? I mean, if you have finite size region, then it will be finite. Yeah.
I just try to see if it's competitive at all.
I mean, I mean, the important, right? So here, what I really want to introduce is a conceptual breakthrough. We really can have transversal non-Clifford case. Yeah.
So I guess for toric code, you have n equals L squared, k equals 1, and d equals L.
Right.
What would the
So this will be similar, except that the toric code you cannot have transversal non-Clifford case in toric code. But here I'm going to show you that you can have transversal non-Clifford case. The important thing is that we can have transversal non-Clifford
but the
case.
scaling is similar?
The scaling is similar. Yeah, we have just a single. I mean, for this particular boundary, I mean, in practice you can conduct many patches together to get more logical qubits. Yeah. Okay, so now let me show you how to get the transversal non-Clifford case. So the transversal non-Clifford case is going to come from automorphism symmetry. So as I showed you earlier, this twisted Z2 cube gauge theory has an automorphism symmetry that changed the green Z2s to be a mixture of other Z2s. So it shifts the gauge field in this way. And this automorphism symmetry is decorated with an alpha. So I'm just quickly, yeah, I think this is the, right. So this automorphism symmetry is decorated with an alpha, which couples the red gauge field and blue gauge field. So let me go back. Okay. And then you can also write down a very explicit finite depth circuit for this automorphism symmetry. So and in the presence of boundary, you also have a boundary contribution, which is obtained by the boundary map, which we study in our paper. So this is the form of the circuit. So you have a bunch of CS and CS dagger. You have for boundary, you have a bunch of physical T gate. You also have a bunch of CNOT gate that implements the automorphism action. Okay. So this is the form of the circuit. And this automorphism symmetry will implement a logical T gate on the logical qubit. So there's a single logical qubit labeled by the holonomy for the bottom edge. So you can label logical states by this number m here, which can be 0 and 1. And this finite circuit will implement the logical T-Dagger gates for this logical qubit. Okay, so this is the protocol. So we first start with Z2 times Z2 torical state, some state in Z2 times Z2 torical. And then we initialize the green qubit as the 0 state, like everywhere 0 state. And then we do code switching to the non-abelian, to this Clifford stabilizer model by measuring this stabilizer pattern for green qubit to convert the Z2 times Z2 torical to be this Clifford stabilizer. And then we apply this T-Dagger gate in the Clifford stabilizer model. And then we just remove the green qubit. We just measure out the green qubit by measuring like poly Z, so the green qubit everywhere, to recover the Z2 times Z2 torical. And then in the end, we'll get the initial state applied by this logical T gate. And because we can do Clifford gates in torical, so we have a universal computation. Because if we want to do universal computation, namely performing arbitrary unitary operators, we just need a single non-Clifford gate. Here we can just use the T gate.
I'm confused. You're already using the logical T. Where did that one come from?
Right. So the logical T comes from the circuit. The circuit comes from the automorphism symmetry. So this is the automorphism symmetry. So V is the automorphism action, which is the CNOT part, and this is the alpha part. The green part is the alpha part. So green part is the like product of like physical CS gate and CS Dagger gate, and this is the form of the circuit. And this blue thing is the physical gate on the boundary. So this physical gate on the boundary arises because you put this alpha on the boundary, you need these boundary terms. So that's the idea. Yeah.
Can I ask a question about this line question?
Yeah.
So we had a similar, the next one, sorry.
The next one, sorry. This one?
Yeah, in our paper we have a bunch of these gates using the double, and we have one procedure that's like the same as this. But we found that if we just don't do this middle step, you don't need to apply the logical T.
Right. So I'm going to compare the approach in your paper with the thing I'm talking about here. So that's the next slide. Okay.
Or is that just applying a possible value to something that's already
Sorry. Can you repeat? Sorry. Can I?
If you do the procedure on the previous slide,
Okay.
you actually need to apply the T gate.
Yeah, we do not need to apply the T gate. So the procedure is slightly different from the your procedure. So that's why we need to apply T gate. Yeah. So let me make a comparison here. So while you're doing this paper, so this is Dominic's and Margarita's paper. Okay. So what they're doing is that they have this code. So this is a space-time picture. So time is going up. So they are doing code switching with these topological domain walls, like this domain wall Planck here and domain wall Dagger here. So your construction can be related to ours by like conjugating an overall automorphism. So we sort of split the domain walls into two. So we have like domain wall and conjugation pair, and then they are related to the domain walls we have by automorphism. So here, this domain wall U is the T gate in this DA gate theory, and here we have two like domain wall and domain wall Dagger, and they are related by some automorphism.
So your domain walls to go in and out of the A are different to the balance.
So here we have the domain wall and domain wall Dagger, like in and out of the DA. But here you have like sort of slightly different ones, because you are condensing different onions for these two. Yeah.
That makes sense.
Yeah.
So if you don't have the unitary and you go back, you would apply identity or
Which unitary? The T gate thing. Yeah. If you do not do anything, then I think you'll just get identity. Yeah. Okay. Yeah. Okay. So we can generalize the SAP to a more general Clifford stabilizer. So for example, one simple generalization is to consider two copies of the Clifford stabilizer models, and I consider a boundary condition that couples the two copies. And in this way, I can have, so first of all, this boundary condition gives you two logical qubits. So for the previous one, I have one single logical qubit, but here I have two copies. So intuitively, you have two logical qubits for this boundary condition. And and can apply the diagonal automorphism symmetry, and that will give you the logical CS gate. Okay, and you can also do similar things for more general theories. So instead of one phone gauge field, let's consider two phone gauge field with a similar cocycle. So it's also a cocycle that couples the three two phone gauge fields. So we have Z2 cube two phone gauge fields divided by ABC, and you have similar cocycles for the two phone gauge field. So the theory is self-correcting because every you have a higher phone gauge series and every excitations are extended, so it's self-correcting. And at the same time, the theory is non-abelian, so the magnetic flux of the theory obey this kind of Brownian ring braiding, and it is non-abelian. So we can perform automorphism symmetry in the theory that exchange the two Z2s. So we have three Z2s. We have three Z2s. Let's consider automorphism symmetry that exchange the two Z2s. And the action will also change under this automorphism symmetry, but it will only change by an exact cocycle. So again, it will change by a d alpha here. So this is the form of alpha. So cup one is some generalization of the cup product, so you don't have to worry about the detail. So the point is that there is a non-trivial alpha here, and this non-trivial alpha tells you that this automorphism symmetry actually can implement a CCZ logical case. It can implement a transversal CCZ logical case in this non-abelian self-correcting quantum memory, and you can also do code switching to like untwisted torical 5 torical to get universal gate. Okay, so let me just briefly mention generalization to higher dimension. So there is a famous theorem proven by Bravia Koenig, who says that if you want to implement a transversal non-Clifford case in the nth level of Clifford hierarchy, you need the space dimension to be at least n. Okay. So here the Clifford hierarchy is defined iteratively. So you heard about Clifford hierarchy like yesterday, but let me just mention a definition here. So the first level is the Pauli operators, and then for the higher level is defined iteratively as operators whose conjugation with the Pauli X give rise to like lower level Clifford hierarchy. So like the second level will be Cliffords, the third level will be like CCZ, T, and other things. So this term is about Pauli stabilizer models. And if we consider more general stabilizer models that are not just Pauli stabilizer, you can generalize the theorem to be a generalized Bravia-Koenig bound. So if you consider a model like a stabilizer model whose component can be like nth level Clifford, whose component can be n-1 level Clifford hierarchy, and you can realize a transversal nth level Clifford logical case in n-1 space dimension. So it's like one space dimension lower, but you have to make your stabilizer model more complicated than Pauli. So for example, we can get a square root of t logical gate in 3 space dimension. So we got a logical t gate in 2 space dimension. We can get a square root of t in 3 space dimension. And I should remark that the model, this kind of Clifford, this kind of higher Clifford stabilizer models, they are non-abelian. But their non-abelian excitations are extended, so their non-abelian excitations are flux of the gauge theory, and in higher dimension they are extended excitations, so they can be corrected by single shot error correction. Okay, so I think I'm on time. So let me conclude. So here, hopefully, I have convinced you that automorphism symmetry in intrinsic gauge theory is very interesting subject to study. So the automorphism symmetry can become extension, or it becomes a higher group symmetry, or becomes non-invertible symmetry. And moreover, automorphism symmetry in intrinsic gauge theory can give you a new construction for transversal non-Clifford logical gates using non-abelian codes, such as the T gate, CS gate in 2+1D Clifford stabilizer model, and CCZ gate in the 5+1D self-correcting quantum memory, which is non-abelian. And for high dimension, we have a generalized bound that generalizes the Bravia-Koenig bound. So let me stop here. Thank you.
Can you go back to your picture where you compare it to Dominic and Margarita?
Yeah, sure.
It's very hard to see, but do you go out again and choose two, right?
Right. So yeah.
What is the difference?
Right. Right. So the difference is how you arrange the domain walls. So in their papers, they have sort of two different domain walls that contains different onions in the middle. And here we have sort of the same domain walls here, and there's a non-trivial like invertible domain wall in the middle. So we arrange the domain walls in a slightly different way, and these two configurations also related by some overall automorphism.
And they're kind of equivalent, no?
Yeah. So I mean, I mean, this T gate is more or less equivalent to
I'm asking a question: is it like conceptually really different, or is it just a slightly different?
So conceptually it is different. So conceptually we have a transversal. So here we are considering transversal gate in a non-abelian topological order, right? So conceptually, the new thing here is that we have a transversal gate, transversal T gate, non-Clifford gate in a non-abelian topological order. Okay. So what they are doing is code switching, like switching between the Z2 square. And moreover, we also have the CS gate, which they don't consider in their paper. So here we have sort of. Sorry?
We do have a CS gate in a different.
Oh yeah, different. Okay, maybe we should talk later. Yeah. So here we need sort of two copies of the D4 or the DA.
Can you go back? So in the bottom picture, it looks like the two domain walls, right? The red guys, and then you can rewrite it as also the product of three things, right?
Right. But it becomes a different domain wall. I mean, it's related to our domain wall by automorphism, but yeah.
In your 5+1D protocol, can you push that down to a 4+1D self-correcting protocol, or is that ruled out by your bound?
So for 4+1D, you can only have a billion self-correcting memory. So if you want non-abelian things, you want to go to 5+1D higher. But if you just want self-correcting, you can definitely do it in 4+1D.
Well, I want universal self-correcting quantum computation.
Okay.
4+1D and 5+1D. Is that impossible, or?
Right. I mean, I think 4+1D should be doable. I mean, I haven't thought very carefully about that, but yeah. I mean, using similar technique, you can probably construct some transversal non-Clifford gates.
But it's not ruled out by your bound.
Right. So for our bound, we are considering one-form gauge field.
Theory just said you can do it.
Mm-hmm.
Your theorem missing the most interesting part, which is this is the best you can do.
Right.
You just say you can do, but doesn't say you have to. So you should work harder to get that part.
I mean, we have constructed a concrete model that realizes the gates. They are just twisted gauge theory with. So they are sort of similar to Benny's construction. Instead of just copy rhetorical, we have a doctrinal twist that couples all the gauge field. So this coupling of all the gauge fields make the theory non-abelian, and also can sort of push the space dimension like one dimension lower. So yeah.
Questions?
Oh, you have.
So when you started with D2 square, you only had one logical qubit, and then you went up to D8, still had only one logical.
Sorry. Which one? So the statement here is right. So if you look at the boundary condition again, you can see that the green qubit does not really do anything. Like you just have the boundary condition for the red. I mean, you can set the green qubit everywhere. Yeah. So you. For this particular boundary condition, yeah.
So how should I? So I just wanted to compare it to the talk yesterday with the hybrid lattices.
Right.
Both have the T gate, but should I think about one as implementing the T gate by using logical gates on physical qubits, which is what you have here, and lattice is more like doing measurements to implement the T gate.
Right. So I mean the questions are slightly different. So here the interesting thing is that we can do a transversal T gate within like a D4 gate theory or DA gate theory. So that's the statement here, and their approach is sort of. Let me show you the picture. Here's the picture. Okay, here's the picture. So the thing we want to emphasize is that we can construct a domain wall that implements a T gate in the middle, okay, within this DA theory. And their approach is more like you just construct 2 domain walls. So we have 3 domain walls, but their emphasis is that you can construct 2 domain walls. Yeah, so that's sort of more the difference. Yeah, the conceptual novelty here is that we have a transversal T gate for this non-abelian code in the middle.
Okay, let's thank Po-Shen again.